Welcome everyone to the 33rd International Material Research Congress Cancun 2025. My name is Muhammad Hasnan Yusuf and I am a PhD student in Culagos, Logos De Moreno. The title of my poster is Synthesis, Characterization and Optimization of FACS PBI3 based metal halide perovskite solar cells for improved stability and efficiency. Starting with the abstract, electricity is essential for modern life, and with growing energy demands, there is a need for abundant, sustainable, and more efficient power source. Perovskite solar cells have shown rapid enhancement in a few years, reaching up to 26% efficiency, but still faces challenges like durability and degradation. Their flexible ABX3 structure allows substitution with different elements to improve performance. Recent research and innovation in this field aim to have low-cost, durable, and high-efficiency solar cells for a sustainable future. The next section is Introduction. The pie chart illustrates the energy demands in various sectors, including 36% for residential sector, 16% for commercial sector, and 48% for the industrial sector. All this energy is produced from different sources like fossil fuel, nuclear power plants, and solar power. If we look at the chart from 2012 to 2022, we see that the energy production from solar energy increased significantly from 2.8% to 12.1%. The limited resources of fossil fuels and their hazardous environmental effect are obvious, causing the world to go for solar energy, which is more reliable and abundant source of energy that is easily accessible to every human on the earth. The cubical representation shows the energy production from different sources. The small red cube shows the annual energy consumption globally. The energy production from wind, biomass, and hydro sources is shown, but they are not accessible to everyone. The yellow cube is the energy that we can produce from sun, that is 80 times more than the global annual energy consumption and is free, ultimate source of energy for everyone. We only need a device that helps us to convert this energy efficiently. The devices used to convert light energy into electrical energy are called photovoltaic cells. When sunlight falls on the surface, the absorbed photon excites electron, causing the flow of electrical current in the semiconducting material. The process is as simple as shown in the figure. Any material that has a structural composition of CaTiO3 is considered as perovskite, and generally it is represented by the chemical relation ABX3. The metal halide perovskites are nowadays investigated due to their long-term durability, stability, and other factors related to a good photovoltaic device. The basic structure of a perovskite solar cell is shown, which has a glass coated with FTO, then an electron transport layer which is titanium oxide, then a perovskite layer, then a hole transport layer which is spirometalled, and finally the counter electrode which is gold or silver. Moving on to our next section, that is methodology. The methodology is how we fabricate perovskite solar cell in the nanotechnology lab of Culagos. First, we cut the FTO glass into equal pieces of 2.5 inches by 2.5 inches. Then we do etching on one side of the FTO with zinc powder and a few drops of HCl. After that, the samples are cleaned and put in the UV for 15 minutes. The TiO2 compact layer is applied using the spray pyrolysis method. After the perovskite solution and spirometalled solution are spin coated for the perovskite and hole transport layers. In the end, a metal evaporator is used to deposit the desired counterelectrode on the synthesized sample. Moving on towards the results. Till now, we have synthesized over 900 FACS PBI3 perovskite solar cells in the nanotechnology lab of Culagos. And initially, we have seen over 20 different parameters that affect the structural, optical, and electrical properties of perovskite solar cells. Working in ambient condition and an uncontrolled environment present a lot of challenges regarding the uniform surface, good brownish color, and degradation with temperature and humidity. Yet we overcome all these hurdles and now we have some best results. Here is the table as an example of experiment design. It has 3 factors and 3 levels, and all the possible combinations from these parameters and levels. Also, for every experiment, we note down the values of humidity and temperature. The possible outcomes while fabricating perovskite solar cell are shown with images. The color should be wine brownish for having the alpha phase, which is photogenerative, while the orange is degraded and the delta phase. Also, there can be a problem of pinholes, center spot, and non-uniform layer. Also, homogeneity is needed for a better perovskite solar cell. Once perovskite solar cells are fabricated, we perform different characterization to check their structural, morphological, and electrical properties. Firstly, the XRD for the structural analysis. We first check the confirmed synthesis of FACS PBI3 perovskite solar cells using copper K alpha radiation having a wavelength of 0.154 nanometer. We keep the 2 theta values ranges from 10 to 45 degree and a crystalline structure is obtained having a highly intense peak at 24 degree. The XRD spectrum well matched with the Inorganic Crystal Structure Database ICSD database code number 250736, confirming the alpha phase of FACS PVI3 perovskite solar cells. We get the 2 theta and full width of maximum values which we use to find the D-spacing using Bragg's law and the crystal size using the Scherrer relation. We get a mean crystal size of approximately 95 nanometers. All calculations are shown in the table. For the morphological analysis, the topographical SEM image is taken showing the big grain size ranging from 130 nanometer to 194 nanometer. And on further analysis, the average grain size is approximately 162 nanometer. And the layer shows clear boundaries between them. The retrodispersal SEM image shows the thickness of each layer in the perovskite solar cell. The thickness of perovskite layer is about 500 nanometers, which is best agreed with the reported literature. For the electrical analysis, we perform JV of the synthesized perovskite solar cells. To find the efficiency of a solar cell, first of all, we place the sample under the solar simulator which is connected to the potentiostat. The light we put on the samples behaves like the sun, resulting in a voltage sweep and current that we obtained from the solar cell. The JV graph shows that sample having less FACS molar ratio has a good electrical response and has a high short circuit current of 15.07 milliampere per centimeter square, open circuit voltage of 0.889 volt and a fill factor of 54%, thus giving us an efficiency of 7.25%. After the one measurement, the sample starts degrading because of the reaction of silver counterelectrode with the perovskite layer. And when we measure one more time, it was degraded, as shown in graph and the images. To avoid the problem of degradation and have multiple measurements, we put the gold counterelectrode on the synthesized perovskite solar cells. Gold is an inert metal and hence it does not damage the synthesized solar cells. Also, we can measure multiple times to check the stability of the perovskite solar cell. The experiment design is shown in the table, having 3 factors and 2 levels. Also, the humidity is high as 70%, and we get a good efficiency of 5.89%. The other samples also shows a good response with gold counterelectrode, a good UV source and less amount of anti-solvent. And the values are shown in the table. The optimization graph shows that the deposition of gold as a counterelectrode helps to prevent the fast degradation compared to samples with silver. The silver reacts with the iodide and makes silver iodide, which causes a rapid degradation of the sample. On the other hand, the gold, being an inert metal, does not react and give more time for the various tests. The stability issues are well overcome by the gold deposition, and overall the perovskite solar cells shows a good response. The conclusion of our overall finding is that by optimizing different parameters and experiment strategies, we have successfully synthesized FACS PBI3 perovskite solar cells in ambient and high humidity conditions without a glove box and show good stability and efficiency. The degradation issue can be tackled with changing compositional ratios, less anti-solvent, and purified lead iodide. Also, the thickness of the perovskite layer and counterelectrode has a direct impact on the degradation and photogeneration. Overall, we improved a lot, and with the counterelectrodes of gold, we can measure JV multiple times and other characterizations.